Hello everybody, in this video let's get into RLC circuits, the natural and the eigenfrequencies, damping and their application as passive filters. When connecting a DC voltage source to a passive RLC circuit, a damped transient voltage appears over the capacitor. The voltage over the previously discharged capacitor jumps from zero to the applied DC voltage but through a damped oscillation. The frequency of the oscillation can be evaluated graphically by measuring the time period of the wave between two consecutive peaks of the transient voltage. The frequency is the inverse of the time period of. Knowing both the value of the capacitor and the reactor involved, the frequency can be calculated as per this formula. The result is the same. For the evaluation of the decay time constant of the oscillation, the following approximation is adequate. It is shorter than the elongation of a straight line between two consecutive peaks across the applied DC voltage line. There's a formula to evaluate the decay time constant, and it is shorter than the rough graphical evaluation previously performed. Let me summarize as follows. First, here is the resonant circular frequency omega for the damped transient RLC circuit. The frequency can be used in the time-dependent function. The voltage as a function of time is equal to the amplitude of the voltage times cosine omega t. Here is the superposition of the cosine function with the original damped RLC circuit. Note that here the DC voltage source has been removed and in return the capacitor has been precharged. The second little circuit at the bottom provides the superposed cosine function. Next, the damping is highlighted by a superposed e to the power of minus the damping constant times t, as demonstrated in the simulation where the exact function is superposed to the simulation. Putting it all together now, the exact mathematical function of the damped transient shown here is superposed to the simulated RLC function, and there is a very small deviation between the two curves. This deviation is entirely removed by applying the more complete mathematical formula below. And by the way, if you want to use the online and browser-based circuit simulator yourself, click on the link in the first comment line of the YouTube description below. So far a DC source was used to stimulate the oscillation of the RLC circuit. Let's replace the DC source by an AC source and watch the reaction of the RLC circuit. Makes sense, right? RLC circuits can be used as bandpass or bandstop filters depending on the serial or parallel layout. A serial circuit behaves as a short circuit at resonance frequency, whereas a parallel circuit's impedance gets very large, ideally infinite at resonance. So a bandstop filter can be laid out as a shunt serial LC circuit parallel to the load. In this example, the load is a resistor. The frequencies around the resonance frequencies are short-circuited and not transmitted to the load. Alternatively, the frequencies around the resonance can be blocked from entering the load by a parallel LC circuit in series to the load. Which one of the two band blocking circuits is used depends on the source and the load impedances. As an example, the frequency band around 2 kHz shall be blocked. For the selection of the capacitor, the inductor is short-circuited by a switch. The selected capacitor of 2 microfarad together with the source and load impedance functions as a low-pass filter, cutting the frequencies above 2 kHz as shown by the simulator. With a given target resonance frequency and the capacitor selected, the calculation of the inductor is easy. The inductor is 3.1663 mH. Now, for demonstration, the capacitor is short-circuited by the switch, and so the circuit acts as a high-pass filter only. But then with both the capacitor and the inductor connected, the blocked frequency band is around the resonance frequency, as expected. So far we looked at the filter in the frequency domain. Now we want to understand the impact of the filter in the time domain. A slight change of the circuit is needed. A 2 kHz 100 volt source is added in series to the existing 1 kV 50 Hz source. A measurement resistor is put in parallel to the source in order to see the total source voltage. Once the filter is on, it is obvious that the load is completely shielded from the 2 kHz oscillation. With the same inductor and the same capacitor as before, the topology is now adapted to a parallel bandstop filter. By changing the value of the load or of the source resistance, the bandwidth of the filter can be adapted. As before, the filter can be analyzed in the time domain. In the next video I will explain a bit more in details how to design simple passive filters, some math needed to do so, as well as some of the risky drawbacks of such passive filters. In the meantime, as a homework, I propose that you design a bandpass filter yourself as per circuit above. That would be a perfect learning experience. There is a link to the required circuit simulator on the first comment segment below this video.